All right, everybody. So, I don't know about you, but does the semester feel like it's going fast or slow? It's somewhere in between for me. But we're about halfway there. I mean, we're at lecture 20 right now. So, you know, we have a spring break the week after next. So, you know, this is week 8. So, this is the start of week 8. So, you know, I guess we'll say this is about the halfway point, which it really is sort of a halfway point in terms of content in the class, because we've got 2 lectures on welded connections, and then after our second exam, we begin sort of the second phase of the course. I would say that the first half of the course is sort of centered around yielding and fracture type phenomena, you know, like gross section yielding, net section fracture, and all that. Once we get into the second half, things change, and we start talking about stability. We start talking about buckling and things like that. And it becomes a different thing. And if you ask me, I think that's when steel design really starts to wake up and get really exciting. Okay. Just to make sure we're all on the same page in terms of schedule, we have our second exam next Monday. Okay. So we're going to review Friday, we're going to exam on Monday, and it's just going to be on bolts and welds. So it's actually the shortest exam in terms of, or smallest exam in terms of how much it's worth. It's only worth 15%. I have had most students say that of the 3 exams that we have in this class, it's the easiest. That does not mean don't study for it, but I think you'll see what I mean. Okay. I would ask how the last homework went, but you didn't have a homework this weekend. So you're going to have a homework today, do Wednesday, one on Wednesday, do Friday. The one on Friday is I'm not going to accept late homework because I'm going to give you the solution to that homework on Friday. Okay? So just throwing that out there. All right? Everybody get the code? Okay. Okay. All right, let me take my little keyboard off here. Set that right there. Okay. Okay. So we had a lot of content in the last lecture that really sort of got to this. Okay. So we had developed expressions for 2 different limit states associated with welded connections. Okay. So, to be clear, we are talking about fillet welds, okay, which is the vast majority of welds that we design as structural engineers. Just like with bolts, when we said, okay, either the bolt can fail or the plate can fail, with welds, we're either saying that the weld metal can fail or the base metal can fail. It's kind of the same idea. For weld metal capacity, what we do is we have our phi value of 0.6, okay. We have our electrode strength times 0.6. Okay, and we do that because we employ an assumption that welds transmit load through shear. Okay, and remember, we can relate a tensile strength of a metal to the shear strength of a metal through the von Mises-Shield criterion, and that ratio is about 60%. As for the area, we take the length of the weld times the effective throat of the weld, and the effective throat is the weld size times the square root, or 1 over the square root of 2, okay? And 1 over the square root of 2 comes from the trig relationship for the geometry of a weld, and that's about 0.707, okay? So that's the weld metal capacity. What about the base metal capacity? Pretty easy. Just either Fy times the gross area or Fu times the net area, but the gross area and the net area are the same because it's a weld. We're not removing material from the gross area to generate a net area. It's all the same. We do have a slight difference in our resistance factors. Well, not a slight. I mean, that's a pronounced difference, but there is a difference. So we essentially, I guess, best way to describe it, we have 3 limit states. Weld metal capacity, base metal shear yielding, base metal shear fracture, and we just take the minimum of those. Okay. Any questions on that? Okay. Now, some additional notes about fillet welds. One of the things that we didn't really talk about was weld orientation, okay? And by that, I mean the angle between the axis of the applied load and the longitudinal axis of the fillet weld, okay? Now, if that angle is 0 degrees, we're dealing with a longitudinal weld like this, okay? Where the welds do primarily, I mean, you can see the weld and the base metals experiencing shear and whatnot, okay? Excuse me. So a transverse weld would be where that angle is 90 degrees, and we're sort of, it's almost like we're yanking on the weld in tension, okay? And so an oblique weld or an inclined weld would be somewhere in between. Now, let me say this. Do we ever see very many inclined welds in practice? Maybe not, but there are some types of welded connections where we assume an instantaneous center of rotation as the weld group experiences failure. And so as you do the math, you do need to account for an angle, okay? So we won't deal with those welds in here. Those are some more advanced welded connections that we would deal with maybe in a graduate steel design course. But just know that there is a way of accounting for weld orientation. Now actually, if you account for that weld orientation and you plot the capacity of a weld as a function of that orientation, you get something like this, okay? So what we've got here are a series of curves that are showing the, on the x-axis, the amount of deformation, how much the weld is deforming. On the y-axis, we're showing how much load the weld can withstand before the weld fails, okay? Now, everything is normalized based off a longitudinal weld. So if you go over here on the y-axis, you can see that value is essentially 1, okay? Now, what's happening as you're increasing that angle is two things are happening, okay? So the first thing that's happening is as you are increasing that angle to going from a longitudinal weld to a transverse weld, you are actually getting more capacity, okay? Now, what that should tell you from a design standpoint is that unless otherwise stated, you would always want to assume longitudinal weld behavior because it would result in a conservative design, right? The worst case scenario for a load in terms of its capacity is if the weld is considered longitudinal. Does that make sense? That's the lower capacity worst case scenario. The other thing that is worth mentioning, though, is how far the curve goes this way, okay? So notice how the longitudinal weld has a lot of deformation all the way over here, but transverse welds do not, okay? Now that phenomenon is called ductility, okay? So what I'm saying is that longitudinal welds present a lot more ductility than transverse welds, okay? So transverse welds are stronger but more brittle. Longitudinal welds, a little bit weaker, but far more ductile. For those reasons, we never want to use only a transverse weld, okay? If I ever see a connection that you've designed in the field and you're using only transverse welds, I'm going to go, nope, bad, okay? Because what would happen is you would take that connection, apply load, you would have very little warning because it wouldn't deform very much, and then it would break, it would fail, okay? That's bad, okay? Whereas a longitudinal weld would present a lot of deformation and get you a lot of warning that the connection is going to fail, okay? So what we're going to do is we're always going to assume that our welds are longitudinal, but then another thing that we're going to do is we are never going to detail a connection that has only a transverse weld, right? I have no issue whatsoever if you utilize a transverse weld in a connection. There's no problem with that, okay? But there better be longitudinal welds to go along with it, okay? So what I want to see is either a combination of longitudinal and transverse welds or only longitudinal welds. If I see only transverse welds, that's, to me, that's not very safe, okay? So I wouldn't use that in most structural applications, okay? And for the purposes of behavior, we're just going to always assume that our welds behave longitudinally. Okay, do you remember that KDS factor? And I said we're always going to assume it's 1. This is what I was talking about. Okay, does that make sense? All right, any questions on that? Okay, so let's talk now, before we get into analysis and design, we need to talk about limitations on fillet welds. And there is an analogy for bolted connections as well. With bolted connections, we said, okay, we have limits on how far apart bolts can be spaced from each other. We have limits on how far apart bolts can be spaced from the edge of a given plate. Those limits didn't really have anything directly to do with capacity. They were more about fabrication and erection considerations than they were about our strength calculations, right? Like if bolts got too close together, you can't get a wrench around them in the field. And if bolts get too far apart, you can get water in between the plates, right? So that's not, I mean, is it something we need to avoid? Yes, but did it affect a PRN calculation? No, it didn't, okay? Make sense? Okay, so there are similar limits for fillet welds, okay? So what we're going to talk about is the limitations on the size of a fillet weld, okay? So the first thing that we're going to do is talk about a minimum weld size, okay? Now, before I talk about the table, let's talk about why there is a minimum weld size, okay? So I'm going to do something a little silly here on the board, but you'll see what I'm doing. Okay, so this is a plate of steel and a plate of steel that I've lapped on top of one another. Let's say this steel is 6-inch thick, okay? So I'm fabricating a Vault-Tec fallout vault, or something, like for a nuclear blast or something. So I'm using plates of steel that are 6 inches thick. That was a joke. But I'm making sort of a point that this is ridiculously thick plates. And we're talking about plates of steel that are like that thick. That's nuts, okay? Now, let's say that I propose to join these plates of steel with that fillet weld. Okay? And let's say that that fillet weld is 1/8 of an inch. That's a really tiny weld for a really, really thick plate, isn't it? Okay? So, first off, I'm going to ignore capacity, okay? Because I'm sure probably one of the main thoughts running through your head right now is that weld probably doesn't generate enough PRN, fillet weld capacity to resist whatever loads have got to be put on it in order to necessitate the need for a 6-inch thick plate. And you'd most likely be right, okay? But my question is there really another issue associated with using a really tiny weld on a really, really thick plate of steel? The answer is yes, okay? The issue is essentially what I'm calling the heat sink phenomenon, okay? So what happens when you place a weld, right? Remember, you have part A and part B. They're clamped together. You have one end of your weld machine clamped to the workpiece, and then when you connect the electrode, you complete the circuit, and energy starts to flow, right? Okay? So if you have this really, really thick plate of steel, okay, and you complete the circuit and begin to deposit your weld, energy starts to flow. But if you deposit a really, really, really tiny weld and then, cut off your weld machine, turn everything off, what's going to happen is this plate is going to rapidly absorb this energy, kind of like a heat sink, okay? And what's going to happen is your weld is going to start to cool, and it's going to cool really fast, okay? In fact, it's going to cool faster than it's supposed to. And that rapid cooling of the weld can result in a loss of ductility in the weld, which we don't really want to do that. We want our welds to be as ductile as possible. So what I am saying is that if you're joining plate A to plate B, the weld needs to be some size in order to avoid that heat sink effect. Does that make sense? Okay? So what I'm saying is, if you look at the plates that are joined, okay, let's say that you have a plate that's somewhere between a 1/2 inch thick and 3/4 inch thick. The weld needs to be at least a 1/4 inch. We need to have at least a 1/4 inch fillet weld so that the weld doesn't rapidly cool and result in a loss of weld ductility because of the heat sink effect. Okay? Does that make sense? Okay? So if we've got this, you know, so if we're welding plate A and plate B together, we need some amount of weld to avoid heat sink. Okay? Sound good? Okay. So that's what happens if the weld gets too small. Okay? Like if bolt spacing gets too small, you can't get a wrench around them. But if the weld size gets too small, you'll have a heat sink effect. What about if the weld gets too big? Okay? So let me replace some numbers here. Let's come up with some numbers that are a little bit more realistic. Let's go with, I don't know, 1/2 and 1/2. So this is something a little bit more realistic. Okay? So I'm depositing a weld, right? So I'm welding this right here. So I'm trying to put like a bead of weld right here. But what happens if the weld gets too big? Let me do something. Let me extend this out a little bit. Okay. So I'm placing weld, right? So as I connect that circuit, I'm depositing weld metal. So essentially this bubble's getting like bigger and bigger and bigger, okay? And I'll talk about multiple passes of the weld here in a bit. But what happens when the weld gets like all the way up here, all the way to the very, very top, okay? What's going to happen is this corner of the plate right here is going to start to melt, okay? And then because this is melting, right, that 45, 90 that you were assuming, and that weld size that you were assuming, suddenly the weld geometry is sort of deformed and kind of weird, okay? So what I'm saying is that if the weld gets too big, okay, you're going to start to melt the plate, and then suddenly that 45, 90 geometry isn't going to be maintained, okay? So here's what the spec says, okay? So what the spec says is they say, all right, okay, if you have a plate like this, like 1/2 and 1/2, okay, what they're saying is like if you want to deposit a fillet weld, let's say here's your fillet weld, what they're saying is the maximum size of that fillet weld needs to be the thickness of the plate, but you need to back it off a little bit. There needs to be a little bit of a gap right there so that at the end of the day, when the weld cools, we can assume that 45, 90 triangle, and we haven't melted this corner of the plate, okay? And that value is a 1/16 of an inch, okay? So that's what's going on right here, is that it's saying that if you're depositing this weld, in order to maintain that geometry, you need to back this off a little bit. Now, a qualifier on that is that this limit right here, is really only valid if the base metal that you're welding to is a 1/4 inch thick or more, okay? So what the spec is saying is that if you're welding plate A and plate B, and the plates are like really thin, like 1/8 of an inch or something like that, spec says, don't worry about it, just fill the whole thing up, doesn't matter. Obviously it could get bigger than the thickness of the plate, but yeah, the spec says, yeah, if you're less than a 1/4 inch, don't worry about it, okay? Does that make sense? So the equation that we'll use is we'll say that the maximum weld size is either the thickness of the plate if the thickness is less than a 1/4 of an inch, or it's the thickness backed off by a 1/16 of an inch if your thickness is greater than or equal to a 1/4. So if your thickness is a 1/4 inch or greater than a 1/4 inch, we got to back that weld size off by a 1/16 of an inch. Okay? Does that make sense? Okay. All right. Now, I'll say this. I just say this to throw it out there. We're not going to employ it because most of the routine weld connections that we would detail would fall well between these limits. But there are limits on both how small a weld can be and how big a weld can be in terms of how long it is, okay? But what I'll say is that for most routine connections in buildings, and the types of connections that we're going to be talking about are things like connecting a beam to a column or connecting a brace to a frame or something like that, are going to have weld lengths that are well between these. So we're really not going to apply them in CE 414. But the long and short of it basically says that a weld has to be at least 4 times its weld size. So if we're depositing a 1/4-inch weld, the weld needs to be at least 1 inch or longer, which most of our welds will be well longer than that. And then there is a limit on the maximum length of a weld. So basically what the spec is saying is that if your weld gets too long, you do result in a little bit of a loss in efficiency, so you have to back off the capacity a little bit. But what I'm saying is that for most of the routine connections that we're going to be dealing with, we're not going to get anywhere near that, so we're just not going to worry about it, at least in this class. Okay? So, excuse me, really all you need to worry about for weld limits are a minimum weld size and a maximum weld size. Minimum weld size you look up, maximum weld size you compute. So this is definitely your Instagrammable, starable type slide for the lecture. Okay. Any questions? Yes.
Is the maximum weld size something you design around, or you design your weld and check?
That's a fantastic question. Okay, and we're going to talk about that next time. Okay. I'll give you a sneak peek into this. Okay, so what we'll do is we'll calculate minimum weld sizes and maximum weld sizes, and what we'll do is select a weld size that's sort of in between. Okay, but I would also say that if we had to choose between a minimum weld size and a maximum weld size, as long as it fit within tolerable limits and what you're able to do on a fabrication side, choose the maximum, okay? And that might seem a little strange, like, wait, did Dr. Mike say choose the maximum? Yeah, I said choose the maximum, okay? Because let me explain why. What we ultimately need to do is supply enough area of the weld to resist the load, okay? And here's what I'm saying. A bigger weld size results in a shorter weld length, right? Just think, if you've got to supply the same amount of area, if I double the weld size, I can reduce the length by half. And the reason why that's important is that the shorter the weld length, the shorter amount of time it takes to deposit that weld, okay? And that means less time in the fabrication shop, less money you're spending on labor in order to generate that connection, okay? Now, there are some caveats to that, which we'll talk about next time, okay? So, about the maximum size that you can feasibly deposit in a single pass and things like that. We'll talk about that next time, okay? But does that sort of answer your question? Yeah. So best I can say is it sort of answered it, because we'll talk about it more next time. Okay. Everybody good? All right. So I got a fillet welded connection I want to analyze. I got a plate lapped on top of another plate. We're going to utilize E70 electrode. Oh, I forgot the electrodes. Dang it, I need to bring them next time. Whoopsie. I'm sorry. I need to bring some weld sticks to class. Okay. So we need to determine the design strength of this connection. We're using A572 grade 50 steel and E70 electrodes. I have the weld sort of indicated right here on the edge, but basically I might not do that in future drawings because I want you to get used to the welding symbols. Okay. All right. So, a couple things before we begin. I want to do is just make sure we're all clear. That on A572 grade 50 steel, this is FY is 50 and FU is 65. I'm hoping you all can find that now by this point. Now, this is the part that's kind of new. E70 electrodes, okay? So if we're dealing with E70 electrodes, okay, what this tells us is what our electrode strength is. So we call that FEXX, okay? And all that is just 70 KSI, okay? E70 are probably the most common, I would say. You might find E60, E80, something like that, but I'd say E70 is probably the most common for structural applications. So, you've done some welding, is that about right?
Yeah.
See, I'm not completely crazy. Okay. All right. So with that, we can start calculating capacity. And again, I really hope that you think after this example that this is easy. This is probably one of the easiest things we'll do in this class, and probably one of the easiest things you'll do in your civil engineering degree is compute the weld metal capacity for a connection like this. Because again, really plug and chug. Okay, so remind me, what's our phi value? We have that. Okay. Now what we got to do is look at this right here. Okay. So, what is our weld size? 5/16. So this number right here is the weld size. Okay. In inches. Now, how about the weld length? This is maybe the only thing that's a little tricky on this problem. How long is the weld? Totally.
15 inches, 30 inches.
But there's two of them, so 30 inches. Because there's a weld here and a weld here. So what this is showing us is that I have a fillet weld that's 5/16 of an inch in size, 15 inches long, but there's one here and here. Okay? So that's what I'm getting at. Okay? So if you've got this, the phi-RN calculation is really easy. I mean, we're basically just multiplying everything together. So, let's see. We've got a phi value, an FEXX, an A value, and a weld length. And so what does that come out to be? I'm going to scooch that up a little bit.
208.79.
So we'll call it 208.8 kips. Do I have a second on that? Okay, got it. Head check. Okay, so like I said, probably one of the easiest things you'll do in your civil engineering degree. It's just multiplying everything together, not that difficult. Okay? What about our base metal capacity? Okay? Okay, so a couple things I'll point out. How thick was the plate on this problem? Was it 3/4 of an inch? What was our weld length? 30 inches. We have that, right? I'm just doing this so I don't have to rewrite. Or sorry, not rewrite. I'm doing this so I don't have to keep scrolling. I'm rewriting it so I don't have to scroll. I got that backwards. Okay. All right, so we have our weld, our thickness, our weld length, and our material properties. So how do we compute our capacity? What is our expression? We're saying, what is it? PRN is the minimum of phi times 0.6 Fy AGV, and phi times 0.6 Fu A and B, right? And the phi values are different, right? So here it's 0.75. Here it's what? 1. So what do we not know in this expression? Like, can we go ahead and compute it now? What are we missing? We're missing those. Now, the first thing to point out is that because we're dealing with a fillet welded connection, they're the same. Okay? Now, what we're asking here, everybody, is how much of the plate has to resist the shear, okay? And I propose the answer to that question is how much of the plate is welded. So what is the gross area in shear or the net area in shear? It is the length of the weld times the thickness, okay? That's how much of the plate is having to resist those connection forces. So in this case, the thickness of the plate times the length of the weld comes out to be 22.5. So here's how I'm going to handle this. So for shear yielding, and so what does this come out to be? So that's going to be our base metal capacity under yielding, okay? So for our base metal capacity under fracture, or rupture, so just change the phi value. and change the FU value. And so what do we get for this? Say it again.
658.13.
So I've got 3 of these values. Which one do I use? Is it the maximum or the minimum? Minimum, because if we're yanking on this, which are we going to hit first? The weld metal capacity. That's going to fail before these do. So okay. Now, this actually wasn't part of the problem. We're going to check weld limits, but before I do, any questions on this? I'm hoping this is easy. I'm hoping this is pretty straightforward. Okay, good. Okay. So let's check our weld size limits, okay? And before I do that, let's just recall that the weld for this problem is 5/16 of an inch. And the plate thickness is 3/4. Notice that, I mean, that kind of makes sense in terms of our weld limits that I would need to know the thickness in that. So let's see what we get. Okay, so first off, a minimum. Okay, now a minimum comes from table J24. Okay. So I'm going to pull this up here on the slide just to make sure that we're all reading it correctly. So, material thickness of the thinner joined part. Again, we're worried about heat sink here, so we just need the thinner piece. But given that we're assuming the thicknesses are the same, so which one do we use? Do we use 1/4 or 5/16? Over 1/2, to 3/4, or over 3/4. Our thickness is 3/4. So which one do we use? 1/4. Okay. So our minimum size is 1/4 of an inch. Okay. So our minimum weld size is 1/4 of an inch. Now what about our maximum weld size? Go away. There we go. Okay. Actually, wait, hold on. Yep, I got that backwards. This one should be less than. That one should be greater than or equal to. I was like, something didn't feel right there. Okay. All right. So our maximum weld size is ensuring we don't distort the plate. So if the plate is less than 1/4 inch thick, we just go with the thickness. But if it's greater than that, we go with this. In this case, we're going to be going with that because we have this. So we have 3/4 is what, 12/16? So that's 11/16, right? So, what can you tell me about our weld? It's good, right? Because it falls between A min and A max. Because this is 4/16, this is 11/16, and then our weld limit, our actual weld size is 5/16. So weld is that. Okay. Take a step back. I'm hoping this is pretty easy, am I right? Should be pretty straightforward? Okay. So, if that's the case, here's your homework that's due Wednesday. Very similar problem, just some slight differences on parameters. Again, I'm hoping that this problem takes you 15, 20 minutes. I mean, it shouldn't be that much work, so this is going to be due Wednesday, okay? Any questions? Okay, so next time what we're going to do is we're going to talk about welded connection design, okay? And specifically, we're going to talk about our process, which our process, I think you could probably figure out the process pretty easily. We're going to figure out the weld size first and then how much weld we need to deposit. But I'm also going to throw a little added topic in there, which is the idea of detailing a balanced connection. But we'll talk about that on Wednesday. That's all I have, everybody. I'm going to pull the QR code up one more time, but I'll see you all on Wednesday.